charge to move on to the Weyl semimetals with Nandini. Let's welcome Nandini.
Okay, good morning. So today I will switch gears from superconductors to Weyl semimetals, but they are actually related in some ways because you can approximatize these Weyl semimetals and drive them superconducting and possibly even topologically superconducting. So that's of course future research. Today I will tell you about these very interesting states of matter, new states of matter that have only in the past few years been observed in experiments, and there has been a lot of theoretical work on that. And I want to give you my slice on how we got into this. So yesterday we were talking a little bit about, some of the students were asking, how do you find exciting problems? And the way I got into this was my student, Tim McCormick, went to the Princeton workshop, a very similar workshop of this kind, and he learned about these topological states and brought that information back, was able to explain to me on the board, and that's how I learned about this. And we also are part of a center where we collaborate with experimentalists, so that was another boost to discovering. One of my collaborators, Adam Kaminsky, discovered the first type 2 superconductor, type 2 Weyl semimetal. I will tell you what these mean, type 1 and type 2, but he discovered the first type 2 Weyl semimetal in molybdenum ditelluride. So in trying to explain that data, we again, got our hands dirty and learned about this. And then, again, as part of this collaboration, I discovered that one of my colleagues in the mechanical engineering department, in fact, does thermomagnetic transport. So these materials have interesting topological signatures that lend themselves to observations through these thermomagnetic transport. So that was kind of, you sharpen your tools and then, you look for opportunities in different directions. Okay, so broadly the outline is going to be, I'm going to tell you about what Weyl semimetals are, and here I want to bring out a few of their characteristics. So I will discuss things like degenerate bands and how that can lead to monopoles. Then the symmetries of the Berry curvature, omega. I'm going to denote that omega of k. Let me also put a band index n. And then the third property will be Fermi arcs and Chern insulators. So if you haven't seen these before, then you will learn about a lot of these characteristics. And if you have, then you can take a little nap there. And in this part, I will then come to different magnetotransport properties. And in particular, I will focus on the thermal conductivity. The other ones are also interesting, various anomalous properties. But because we have limited time, I will just focus on one transport coefficient, but it's, I think, one of the most interesting transport coefficients because it targets the entropy transport, and in general, transport coefficients are always messy because everything contributes. And somehow you have to separate out what is the things that are not dominated by the bulk and so on. But in general, the thermal conductivity will have pieces like the bulk piece, and a more topological piece, and I will try to bring that out. These are tensors, so I'm just kind of schematically showing this. Okay, so that's the broad outline. Now, So let me start with writing the, let's push this up. So essentially a Weyl semi-metal has these Dirac-like cones with linear dispersion. So this is, let's say, Kx, Ky, and Kz. And let me just draw energy here. So I've suppressed Kz, energy as a function of Kx and Ky. And in the bulk, you have these linearly dispersing spectrum at some point K0 and minus K0. And if you expand the Hamiltonian around those Dirac points, then the Hamiltonian is given by some velocity K dot sigma. So these materials have strong spin-orbit coupling. Sigma here I'm going to use as real spin, not some pseudo-spin, and K is the momentum. And so K dot sigma depicts the spin-orbit coupling. And chi is the chirality. So this is the Weyl fermion. It's obtained from the Dirac, the four-component Dirac states, and that's where you get the chirality. And it essentially gives you an idea about how the spin is twirling around the direction of the momentum. So positive or negative. So chi can take on two values plus minus. Okay, so one of these is chi equal to 1, and the other is chi equal to minus 1. So that's essentially what we call a Weyl fermion. It's a relativistic fermion with chirality. Okay, now that's in the bulk, and it will have interesting bulk boundary correspondence, and for that I will take a slab geometry and show you how that comes about. But first let's play with this Hamiltonian a little more. So let me just take one of the nodes and let's write this out. Sigma here is the Pauli matrix. So K is a three-dimensional vector. So here this is important to stress that Weyl semi-metals I'm looking at are in 3D. It's kind of the 3D analog of graphene, you can think of it that way. So in graphene, K would have been just Kx and Ky. This is a 3D vector, Kx, Ky, and Kz. And that will be important. And sigma is the Pauli matrix, sigma x, sigma y, sigma z, which as you know is so if I combine this, then we can write the Hamiltonian as V right? And this, this is essentially like a spin in a magnetic field, except the magnetic field is changing with K. So it's just a two-level system, and its eigenvalues, P plus minus, are V okay. So for each chirality, you get two bands. And these two bands, let me show in two colors actually. this is E plus, and this is E minus. Now, this is where the distinction with graphene becomes important, because in general, if you have two bands, right, you can, if you have the touching of two bands, they can mix and open a gap. That would be the standard thing that would happen. Now, in this case, you can see that in graphene, if I just have these two pieces and say Kz is 0, then you can put any kind of a mass term and open a gap at the crossing. But here my momentum is a 3D vector, so all you can do is you can move the Y point around anywhere in the Brillouin zone, but you can't ever open a gap. So that's the important thing about these Y points, that degeneracy point is protected. Okay, so that's the structure of the eigenvalues. We can look at the eigenvectors, and that's just a spinner on the up spinner and the down spinner, and this is just your usual cos theta over 2 e to the, and I've just chosen phases to be in some symmetric way, but you can choose different gauges for the wave function. And a similar one for the minus state. Okay, orthogonal one. And so this spinner then describes, so what are thetas here? I have parameterized my vector k in terms of the angle. Sine theta cos phi. Okay. Okay, good. So that would describe the actual spin structure at each k point. Okay, now comes one of the most central properties of a Weyl semimetal, and that is the existence of a monopole just at the sort of located at the degeneracy point. So I'm going to come to this point number 1. Okay, so we have the wave function. Essentially, we can calculate the Berry connection, which is the vector potential. So you start at some, you're essentially starting at some point in k space, moving around, coming back, and asking how much flux did you pick up. So the Berry connection is the vector potential, and so I'm going to sit on one of the bands. So let's say on the up band, the red band, and n denotes is going to be either the plus state or the minus state. That's what n is. And I want to evaluate the overlap of the state at two nearby points. So if you take that state, and I'll let you actually work out the details, but if you take that state and just evaluate this, putting that spinner for the up state, then what you get is okay. And actually more useful than the Berry connection, which is gauge dependent, is the Berry flux, which is, or the Berry curvature. Which is just the curl. It's just like your standard electromagnetism. It's the curl of A. The only difference is that we are used to these fields in real space and taking curls in real space. Now what you have is a magnetic field in momentum space. And that's coming about because of the spin-orbit coupling. So when you work this out, then you find that omega plus at each k point is singular at k equal to 0, and the singularity is that of a monopole. And similarly, the other state, the down state, has a negative monopole, has the opposite monopole. It has a plus. Okay, so it's a very direct calculation from the state. You can just evaluate this, and that's a direct consequence of that degeneracy. You can also get this from another related definition of the Berry curvature. I won't go through that, but that definition involves now the Hamiltonian. Here I have operated it and obtained it using the wave function. You can also transform it to the Hamiltonian, and you get a very nice expression which leads you to Hall effect and so on. But that is another way to get exactly the same result, but using the Hamiltonian as in the definition for the Berry curvature. Okay, good. And so this is what is happening on one of the nodes, one of the Weyl points, and it will be the opposite situation on the other Weyl point. I'll mention that a little more later. But let's now pay a little more attention to this Berry curvature and ask what kinds of symmetries does it have under time reversal and inversion. Leon has a nice article where he calls this when the Weyl points kiss. So that's the kissing of the Weyl points. Beware, there's a monopole sitting there. Okay, symmetries of omega of t. I'm suppressing the band index, but this is always defined per band index. And the reason is, whenever you evaluate a Berry curvature, you have to do it adiabatically. You have to sort of follow a band and see how your spinner is rotating. And here they are touching, and at that point, the gap is, that's one of the reasons why initially people were surprised that you can even have a topological semi-metal. Because in a topological insulator, the gap is very clearly protecting your bands. And you can follow one band all along that adiabatic route without ever closing the gap. Here the gap closes, so at that point you have to go infinitely slowly if you are trying to stay on one of the bands. Okay, so now let's look at these two symmetries under inversion and under time reversal. So let me put it here. So under inversion, R will go to minus R, K will go to minus K, and spin remains unchanged. Now, perhaps the best way to see these symmetries, I have to get rid of this, is to look at these equations of motion. The semi-classical equations of motion, they change in a very important way because of the presence of this Berry curvature. So what you have is K dot is the changes due to an electric field and the Lorentz force. So this is the external magnetic field, B. And R dot is Vk, which is just coming from the band structure. So Vk is the gradient of the band structure, epsilon k, plus now this new term, which is K dot cross omega, omega k. So there is a very nice symmetry between these two. You can write this E also as a gradient of the potential. Here you have gradient of E and a K dot cross Berry curvature, just as here you have R dot cross B. So it has this very nice symmetry. And it's useful to look at this to also see how R dot and so on will change. So you can similarly go on and show that R dot will change to minus R dot. That's just coming from the change, that's just coming from the change of R to minus R. You have K dot going to minus K dot and Vk going to minus Vk. So why am I doing all this? I'm doing this because I want to understand these two Weyl points that I have. I want to understand how the Berry curvature is distributed across these two Weyl points. Okay, and on the time reversal side, I have R going to R, K going to minus K, and sigma going to minus sigma. And if I look at the dots now, the rates of these vectors, R dot goes to minus R dot. K dot goes to plus, because there are two sign changes from the time part and the K part. So there's a plus here, and Vk goes to minus. Okay. And from this, what you can show are these important results, that when you're looking at inversion, essentially, to make the left and right side agree, what you get is that omega of k is omega of minus k. Okay, under inversion. And under time reversal, the Berry curvature changes sign. I should say it goes to this under inversion. Okay. And of course, if you have both time reversal and inversion, then the Berry curvature is 0. So what you end up getting is, in terms of the Weyl points, so in terms of the Weyl points, then the minimum number you can have, this is now looking at one of the bands. Let's say I have, so under time reversal, if I'm looking at a point here, it maps into another point there, and the Berry curvature at these 2 points, the omega is either it's positive and negative. So on a single band, you get 0. So the minimum number of Weyl points you need are 2 Weyl points under time reversal. So under time reversal, this is the minimum you need. Now under inversion, what you get is this K point maps to that K point, but omega remains the same. It does not change sign. So if you want to get a net flux of 0, you must have another Weyl point and its map with negative curvature. And that's how you will end up getting a net Berry curvature of 0. So this is under inversion.
Sorry, Nandini, just to make clear, I'm not sure it was said quite clearly, but the left-hand case with 2 Weyl points, that can only occur with broken time reversals.
Yes, sorry, I'm trying to break. Sorry, I should say time reversal breaking. Yeah, sorry. And thank you so much. And this is with inversion breaking. Yeah. So the minimum number of Weyl, so let me say that again. So if you have both time reversal invariance and inversion symmetry, then the 2 points that I showed you in my initial band structure, they would be degenerate. That would be called a Dirac semimetal. So you have to take a Dirac semimetal and break one of the 2 symmetries. If you break time reversal, you get the nodes separate, and you need a minimum of 2, and you get a minimum of 2 Weyl points is what gets generated. If you have inversion breaking, then you need a minimum of 4 Weyl points. That's the statement. Okay? Yeah.
In case of graphene, that's a 2D case. So in that case, when we break inversion symmetry, we put a mass on 2 points, and they break into the exactly 4, the K and K prime point, both breaks into pieces, and we end up with 4. That is exactly what you are trying to write when you are talking about it.
So no, I'm not doing that. Here there is no mass. Okay, as I said, graphene would be something like kx minus iky and kx plus iky on the off-diagonal terms, and on the diagonal you would have a constant, right? And that would open a gap in the spectrum. Here you still have a Weyl point, they are just moving around. So it's not opening a gap, unlike
so how you are breaking the time reversal symmetry in the Hamiltonian level?
Here?
Yes.
Here so in this case, I have just written, so in a real system, you would have some magnetism, let's say, and that would break time reversal symmetry. And then I would get, the Hamiltonian I wrote down was actually a minimal model for a time reversal broken with 2 Weyl points. That's actually the Hamiltonian I wrote down was for a time reversal broken system. If I was writing it for an inversion, I would have to write 2 more Weyl points, which I didn't do. Okay?
So the Hamiltonian we started with as a tiny version.
Yeah, I started with that just to keep it simple, with 2 Weyl points. Currently, most of the materials that have been found are the inversion breaking kind. So you would have to expand it. Yeah, sorry.
It might be worthwhile to make a comment.
Yeah.
I wonder, the symmetry arguments kind of tell you something, but you might wonder why you can't have just one. And suppose you had no symmetry at all.
Right.
You could break both time reversal and inversion, and there's really a topological argument
That I
why
think
they
goes
have to come
back
in
to
pairs.
that's the Nielsen-Denomia
Yes.
statement. That is actually important. I should have said that at the very beginning, that I said that you get a chirality, chi. And as Leon says, why could you not just have just a positive chirality? And that comes from, it's like Gauss's law. You are looking at the total flux across the entire Brillouin zone. And there's an argument by Nielsen and Denomia which just builds on this aspect, that the total flux must be 0. So you must have these Weyl points of opposite chirality. They must come in pairs, and they must have opposite chirality.
So what is about this chiral anomaly? Is the breaking of what you had argued, or is
Yeah, so there you can now, you can pump charge from one node to another. You need a E dot B term, which is a chiral anomaly which can pump charge from one node to another. But yeah, if you don't have this, if you don't have a net chirality of 0, then then you violate gauge invariance. So it's a very deep reason for requiring a total chirality of 0.
But in this Hamiltonian that we wrote down, we haven't talked about any.
I'm sorry?
The Hamiltonian we started with, we haven't talked about the gauge.
No, I don't need to talk about that at the Hamiltonian level. When I pick the wave function, then okay, I haven't applied a magnetic field yet, I will come to that. But in the wave function, you can pick a gauge. But in the omega, it's gauge invariant.
Right.
Okay, so that's as much as I wanted to say about the Weyl semi-metal. Now I want to use this semi-metal and see what kind of properties it might have. So clearly, one of the interesting properties is how to observe the Berry curvature. And you can do that through a number of anomalous Hall effects. So, just like in Hall effect, you have, say, electrical current flowing in, say, the x direction, you apply an external magnetic field in the z direction, and you get a voltage in the transverse direction, the y direction. And now you can see anomalous effects, and by that I mean you're not going to apply an external magnetic field, you're just using the magnetic field of the Berry curvature and using that to produce an anomalous response in the transverse direction. So, I'm just wondering, maybe I should, okay, let me just say a little bit and then quickly move to the thermal conductivity. So what you have is a charge current and a heat current, and these are coming from these matrices which or these tensors which tell you how they couple to either an electric field or a thermal gradient. And you can also actually put spin on the same footing and put a chemical potential for spin. And so there's an ensemble relation which puts LTE equal to T times LET. And the important thing, and I won't do too much of that here, But the interesting thing is in each of these, so in LEE, there is the off-diagonal term, which is LEE is essentially sigma, the conductivity tensor, and the off-diagonal term in that is the Hall conductivity. Similarly, in LET, there is an off-diagonal term which you can, which is the, so the off-diagonal term here is called the Nernst effect, the Nernst coefficient, and in LTT you have the off-diagonal piece is the thermal Hall effect, which is playing an important role right now in some of the spin liquid measurements. My main purpose of bringing this up is that when we look at thermal conductivity, which is the diagonal piece of, or any of these thermal coefficients, we want to do it under conditions that the charge current is 0. So if I want something like kappa, which is this thing, it is LTT, but there's a correction to that, which is LTE E minus grad T. And yeah. And this is actually related, okay, there. I think that's good enough. I want to just make 1 or 2 points. In these multi-band systems, it becomes really important to look at 2 aspects. One is that these additional terms start playing an important role. What we are saying here is that the thermal conductivity, this coefficient here, is being, you can drive a heat current in 2 ways. Either by applying a thermal gradient, but also by the chemical potential that gets generated when you apply a thermal gradient. So you're not applying an electric field. You're applying only a thermal gradient, but you want to evaluate this under conditions that the charge current is 0. When you do that, that automatically generates a chemical potential gradient. And so that is the origin of this term. This is often called in the literature antipolar terms, and they can be really important in these semi-metals. So I don't have time to go into this, but we have looked at a lot of data on niobium phosphide and various other semi-metals, Weyl semi-metals, where this term dominates the Nernst coefficient and also thermal conductivity. So in other words, bulk thermal conductivity is quite complicated to analyze. So what we want to do is to kind of move in a direction where we can actually focus on some just essential pieces of this topological structure, which is not burdened by so much of the bulk. And this is where I now come to the Fermi arcs.
Excuse me.
Yeah.
Could you explain what is the delta T inverse?
I'm sorry?
What is the inverse of the vector?
No, it's a, sorry.
That's what that is.
You can just write it like this if you want. You're just, it's a tensor, so you can, if you want, you can just write it as, put some mu's, take a mu like that. That may be better. So you can just write this as kappa mu, jq mu. Like that. Okay, so now let's come to the Fermi arcs. So at this point, what I want to do is take that system, the periodic system, and put a boundary. So here is kx, ky, and the z direction it is finite. So my energies are now kx, ky, and it has some band index n. Now if I look at now my surface Brillouin zone right here at 0 energy, then each of these points has a projection on the surface, and between those points you get a set of states that exist at 0 energy. And the way you get this, I've run out of time a little bit, but the best way to see that is to put, this is essentially a Dirac spring between the plus and minus monopoles, and at each, you can make a slice at each point between these two monopoles, and this is like a quantum Hall plane with a magnetic field pointing out of it, which drives essentially a chiral state around it, just like a quantum Hall chiral state. And that chiral state then in the Brillouin zone of the surface, which is kx, ky Brillouin zone, gives you 1 point. And as you make many slices here, you get all these different points which map out an arc. So that's a Fermi arc. And you get a similar Fermi arc on the bottom surface. Okay? So that's the structure of a Weyl semi-metal with broken time reversal invariance and a finite slab geometry. Okay, so if you look at the dispersion of these Fermi arcs, so in ky, so now what I'm doing is I'm plotting. It's useful, I can give you a mathematical notebook, you can play with it and see the different cuts. But if I look at now the energy as a function of ky, then what you get is you get sort of these bulk bands. So what I'm doing is I'm sitting at some kx, so fix kx, and look at it as a function of ky, and what you get is a chiral state on each surface. So let's say this is on the upper surface, and on the bottom surface you get a similar thing dispersing with the opposite velocity. So that's on the lower surface. So I don't want to mix it up. This is not the Weyl, it looks like the Weyl point. Let me just make a separate figure here. So this is as a function of ky on the bottom surface. This is energy. Okay, now we are almost getting there to the more interesting and new part of looking at how heat would be transported here. So what I want to do here is look at thermal conductivity when a thermal gradient is applied in the z direction and a magnetic field is also applied in the z direction. Okay. So both are along z. B is parallel to z. So this is my z direction.
Excuse me. just to make sure that this is all kz equal to constant value we are looking at.
Kz is now no longer a good quantum number, okay, because I have a slab geometry. So kx and ky are still good quantum numbers, but not kz. I have some discretization in this kz direction. So for this case, I'm looking at some fixed kx as a function of ky. So what I'm doing is trying to get, these are my Fermi arcs, and I'm describing the velocity of an electron on the Fermi arc. And essentially what I'm saying is that electron, if I look at an electron here, it has a velocity in the y direction, ky. So if I see, the way to think about this is to think it's useful to think in the semi-classical picture where each state is described by k, r, and t. And if you look at dk dt now, this is going to be E over C bk cross b, and that gives me E over C v b in the tangential direction, or you can call it, this is along the arc. Okay, so that's the one important point, that if I look at an electron, so what I'm trying to do is the following. I want to figure out how does this electron move under the influence of a magnetic field. Okay, and what it experiences is a Lorentz force, which pushes, because the velocity is in the perpendicular direction to the arc, v cross b, b is in the z direction, pushes the electron along the arc. Okay, so there's a force pushing the electron along the arc. Now, so you start with an electron at this k state, it keeps moving until it reaches that node. Okay, so the second point I want to bring up is how these states behave, the wave functions behave in the z direction. So if you look at psi as a function of k parallel at z, then as a function of z, it decays this is at any point away from the node, away from the projection of the node, and at the node, it decays into the bulk. So this is at the node. So you see, what you have is in the bulk, when you're at any point in between the two nodal projections, there is a gap in the spectrum. And as a result, the wave function decays on some short length scale. So the electron is mostly on the surface. But when it reaches this point, the wave function now decays into the bulk. Okay? So what it generates is a connection between a surface through the bulk, and then it connects to the other surface where it is pushed in the opposite direction. It's pushed in the opposite direction, and it closes the loop coming back to the top again. So this is a very interesting pathway that connects a surface state, a topological surface state, through the bulk monopoles to the other side, to the other Fermi arc, and then back again, this particular circuit. Is everybody good with that? Okay. So this is the channel I'm going to exploit now and calculate the entropic transport around that. Okay. So actually running out of time. But that's really the main idea that I just put out. So we just looked at the charge part. Now we can look at the heat current, JQ, JZQ. And this is going to be essentially the number of electrons that are transported per unit time and the energy across the two surfaces. So let's say I'm sitting at z equal to 0, here's the box. I'm sitting at z equal to 0. This is the thickness, L. So you're looking at U at the energy density at N over 2 minus the energy density at minus L over 2. And this can be written as du by dt, dt by dz. And this just becomes part of the gradient of the temperature, and so the thermal coefficient is whatever is left there. And these terms can be simplified. Essentially, dN by dt can be written in terms of the density by dE, dE by dk, and dk by dt. I'm going to be a little quick and not too precise, just to give you the idea. This is just the density of states, G on the arc. This is basically H bar Vf. And the density on the arc you can show is the length of the arc, K0 over H bar Vf. Okay, and dk by dt is the rate dk dt we just evaluated there. This is E over C VB. So if you put all of this together, and so that's what we have for this term, du dt is nothing but the specific heat. This is the specific heat, and that can be also kind of easily evaluated. These are standard things you can do from Ashcroft and Mermin. This is the specific heat of the bulk, and that part can be shown to be, so let me just roughly say what you get. This would be, Kb sets the scale, and it will, the bulk, G bulk, in fact, goes like E squared. So with that, you can show that this will go like kBt over H bar Vf, V times gamma. So this lambda, this is a cutoff. So I showed a linear dispersion. That linear dispersion continues up to some cutoff. Beyond that, there are curvature corrections. That's that cutoff. So this cube is what you get for the specific heat. So you put all of this together, and what you get then for the thermal conductivity is, so then you get kappa, Z, Z, Z. This is the simplest. This is the direction of the gradient. This is the direction of JQ, and this is the direction of the magnetic field. And that turns out to be KB VF. That's setting the scale, and then you get KBT over H bar VF cube. And LB is the magnetic length, which is basically EB. Okay, and it's just in terms of, if you want some numbers, this is about 25 nanometers with B in Tesla. Okay, So the key things I want to bring out is this scale that is set here is about 100 watts per meter per Kelvin. And everything is there, but look at this term here. This is proportional to L. So it's indicating that it's like a conductance channel, like a 1D conductor. And so it grows with L. So essentially, this is where, what will help the observation of this phenomena. That, these are all suppressing aspects. It's T over lambda cube. I've run out of time a little bit, but just to compare this with free electrons. This coefficient in free electrons, it has a very similar structure. The thermal conductivity goes like the specific heat, a velocity, and a mean free path. And if you put it all together, you get a prefactor which is about the same order of magnitude. Here, instead of a power of 3, you get a power of 1, kBt over EF. This is much more suppressed, but what buys you a big enhancement is L over LB. So we think this should be observable. Another important point is, this is the arc-mediated part of the response. But there's that whole bulk thing I talked about. So the way you can separate these two is just change the direction of the magnetic field. If you put the field in the direction of the separation of the Weyl points, this channel gets blocked. So this is an additional thermal conductance channel over and above the bulk conductivity. So that's one way to separate it out from all the bulk. The other thing is there are lots of phonons all the time, which will obscure the features, and that can be separated out because phonons don't depend on the magnetic field, whereas this thermal conductivity will be proportional to the magnetic field from these two factors. So that's another thing. I have run out of time, so I can't discuss the high field regime, which is also interesting. That's in the regime. This was all done semi-classically. The important thing here, if you have read the Potter Vishwanath paper, the difference here is you don't need any coherence to see this effect. All I have used really, that's why it makes it a very powerful argument, is the continuity equation. So you have your electrons being transported along the arc, they reach the nodal point, and they have to leak into the bulk, and even if there is scattering. So you can have scattering which is within a node. So long as you don't scatter from one node to another node, this channel does not get obstructed. So even if there is scattering, think of a pipe carrying water where the molecules are bumping around, within a pipe. That pipe has to flow through the nodes to the other Fermi arc, even if you have scattering. Intranodal scattering. So it's robust against all of that. In the extreme quantum limit, the Weyl points also become chiral. And I think I'm going to stop there. Just you can look up the paper, and then you can rederive all of this. Very similar structure, except that once your Weyl points themselves become the bulk band structure changes, and now you get around each point, you get around each Weyl point, you get these Landau levels, which disperse now along. This is Kz. Because in a magnetic field, now even Kx and Ky become discrete Landau levels, and the only good quantum number, if at all, is Kz. So you get this kind of spectrum, and that changes the specific heat and so on. So these dependencies on B and temperature change, and the scale is now set by the quantum of thermal conductance, which is, that's kind of useful. So this is now in the quantum regime, kappa, the scale is set by GQ. GQ times some different dependencies. Basically, it goes like T, and it goes like B squared. So it's a different dependence from here, T cube and B goes like T and B squared, and GQ is a number, pi squared over 3, that's not so important, but kBT times kB over h bar. That sets the scale. So okay, that's basically the story I wanted to tell you about. Maybe we can take more questions. Thank you.
Questions?
Yeah.
So if I turn off the magnetic field, I don't get any thermal conductivity from these modes?
So you still have the bulk thermal conductivity,
Yeah.
but this arc-mediated channel now is not available. So the key point here was that this charge is actually not being transported. There's no net charge transport. So if you take any plane, you have charge moving up and charge moving down the other node, and so there's no net charge transport, but heat is being transported from the hot end to the cold end. So this becomes a kind of like a heat switch. You can turn on and turn off that heat conduction or entropy conduction by turning off the magnetic field.
And is there a way to think of, so electrons going from the hot region to the cold region, and in the one direction, they're, can I think about it? How do I think of the thermodynamics sort of going on? How is that heat
It's
being?
useful to make two pictures in your mind.
Yeah.
That's one is a real space picture and one is the momentum space
Yeah.
picture. So in real space, there's no the channels are all in momentum space,
Yeah.
right? In real space, you have like a plane, and then things are sloshing back and forth on the planes, different slices along the z direction. But in momentum space, it's exactly what you said. You have, you are looking at where is that k point and how is it moving in k, and correspondingly what is happening in real space. So if you look at, let's say, a zero energy, so look at that slice. The states at zero energy exist in two places. One is in the bulk at the Weyl points, and the other is on the surface on the arcs. And in a magnetic field, you transport the electrons on the surface, and while they are on the surface, at some general point, they are not leaking into the bulk because it is gapped until you reach the Weyl point, the projections of the Weyl points. Then it leaks.
In the case where you have more than just a single pair, can these Fermi arcs interact at all or do any interesting things like that?
Well, so you've already, so the Fermi arcs at this are, it's a non-interacting band structure that has given you whatever number of Fermi arcs. If you now further do something to it, like say you proximatize it with a superconductor, then you can have mixing of electrons in different arcs. But the starting point is this non-interacting band structure with whatever pairs of arcs you have. But yeah, you can perturb it with other interactions. Yeah.
Sorry, I snuck off to the bathroom at exactly the wrong time. So
Oh.
I think I missed some of the key things. So K here, is it a conductance or conductivity?
Okay. K is so K K is a conductivity, but because it has this 1D nature, it is proportional to L. So really one should think of it as a
Which L? So
the LZ, sorry, it's the thickness of the sample. So you should think of it as a conductance with L defining the thickness of the sample. So it's coming in,
So you would have thought that some effective currents flowing at the surface would lead to something that's kind of a small current density in the bulk. Is that
So
not-
there is that too. So if, I forget all about this, but if I just change the magnetic field direction, I will have some surface currents which will flow and give me some conductivity. So this is now an additional contribution that is coming from more like a 1D conductance channel that has opened up.
But the picture is you have some, maybe I should ask you offline, but you have some quasi-particles flowing along the arc driven by the magnetic field.
Exactly.
And they get pushed into the bulk, they have nowhere else to go.
Right.
So then you need to count how many, what's the current of these quasi-particles flowing along the arc.
Right.
That should be, I would think that's independent of the thickness.
Right. So that's that.
That doesn't depend on LZ.
That doesn't depend on LZ. So that's just the current, the dk dt is just the current flowing along the arc.
Mhm.
Then LZ comes in once it traverses the bulk to go to the other side, and then you are looking at the heat flow across that thickness, and that's where you get the heat on one edge minus the heat on the other edge, and that brings in an sort of a L/2 factor. So it's like if you were doing a standard conductivity, you would have had something like a mean free
So
path.
would the L drop out if I expressed it in terms of the temperature difference between the top and bottom layers, rather than a temperature gradient? Is it?
So the temperature gradient is still there, but this is an additional factor that comes in. Maybe we can discuss this later, but it doesn't drop out. And that's a reflection of the fact that you have a conductance from this 1D channel. So, if you had, in other words, a 1D conductor, which was kind of a perfect conductor, the thermal conductance would have had that L factor there. The point here is it's not perfect. It has scattering. So why does that not affect it? You might have thought there should be some mean free path which is providing a cutoff. And that doesn't happen because of this very particular directed motion of these electrons down that channel. And it's driven by the continuity equation because these electrons have to go somewhere. They can't be lost. So you don't have a mean free path limiting this effect. And you don't need coherence. So that, I think, is important. Now, I should also add, this effect has not been measured. So several of the other things that I mentioned, that the Berry curvature can be related, can be observed through a Nernst coefficient or through, even the Seebeck effect, can see the Berry curvature. Those have been measured in our group itself and many other groups in niobium phosphide and other materials. But this effect is really a prediction, and we are hoping somebody will measure it.
I have one question. So this is, you kind of addressed some of my questions, but there are a lot of people doing measurements on these Weyl semimetals, and are they all RPES or transport? And what kind of debates are there? What's like smoking gun? Just
Right.
like, from outside, there seems to be a lot of noise.
Right. So I think the key things people would like to measure are some quantized signatures of these Berry monopoles, for example. So let's go step by step. So the Fermi arcs are ideally suited to be observed by RPES, because RPES is a surface-sensitive technique, and that's how it has been observed. So, and there are two kinds, I alluded to that in the beginning, but there is a type 1 and a type 2 Weyl semi-metal, and maybe let's not go into that detail, but in any case, for both of these, so essentially in type 1, I showed you these two cones that touch at the Weyl point, and that can be thought of as a direct band gap semiconductor coming and touching at a point. Okay, now if you have an indirect band gap, so you have sort of a conduction band and a valence band, and now you bring them and say it's a compensated semi-metal, then in general you will get an electron pocket and a hole pocket. But you can, if these two pockets touch at a point, that becomes that becomes like a tilted cone. It's like these two cones are touching, but there is a tilt. And if you have a tilt, so it's a bit like this, and they touch at this point. So if you expand around this point, it's like a tilted cone. And that's a type 2 Weyl semi-metal. So MOTE2, WTE2 are all examples of these type 2 Weyl semi-metals. So there's been a lot of work just getting the Fermi arc structures in these Weyl semi-metals. Yeah. Then there's been transport, and that has been focused on things like the Seebeck effect or the Nernst effect, where the main point is, so if you look at the chemical potential in these systems, you know, they're not always going to be at the Weyl point. You'll have some chemical potential somewhere in the band. But as the temperature is changed, you know, we are used to just setting the chemical potential at EF. But in these multi-band systems, how the chemical potential moves is a very important part of the thermodynamic behavior, or this transport behavior. So what will happen is the chemical potential moves from the band position to the Weyl point. And when it does that, it picks up the maximum effect of the Berry monopole. So you end up getting peaks in your Nernst coefficient as a function of temperature. And then you need some theory to understand why this is happening, but that, if you model it, can be interpreted as coming from these monopoles. So that's one direction where there's a lot of work.
Maybe I'm vaguely remembering magnetotransport.
Pardon?
Magnetotransport.
Yeah, so that's all of those L's.
These are all.
All these L's are part of the magnetotransport. And the key thing there is to somehow look at anomalous transport, because otherwise, you know, you don't want to deal with scattering rates. That's a mess. So you want to look at these anomalous transports that are essentially, so for example, the Hall effect, sigma xy, is an energy integrated quantity which looks at the Berry curvature, omega times the Fermi function. Okay, when you integrate that, that gives you the sigma xy. If you look at something like Nernst, it's the entropy at each energy slice integrated again. So these integrated quantities will never give you the just the Berry flux, but the integrated quantity will be probed by thermomagnetic transport. And I've tried to go one further step, which is to say, well, the arcs are really the most exciting piece of this Weyl semi-metal, and really the arcs don't exist by themselves. There's an important connection of the arc and the Berry monopole and the other arc. And exploiting that channel will give a yet more unique signature. Yeah.
Student priority.
Thanks. If I understand it correctly, you are saying that if I like elongate this slab in the z direction,
Yeah.
the conductivity in the same direction become enhanced?
Yes.
Isn't it a little bit counterintuitive? Because I mean,
Yeah, it is counterintuitive, and we did mull over it a lot. Now you might say, you know, make it the size of the universe. The point is, ultimately there is phonon scattering, which will scatter from one node to another node. So you will be limited. I should put a cutoff at at whenever internodal scattering will kill this effect. So that is a cutoff.
Dan?
You've talked about heat transport. Are there analogous, interesting anomalous behaviors for spin transport too?
Yes, we haven't investigated that. Mainly because I don't understand spin chemical potentials. That is where I am stuck a little bit. But you can expand these equations to add chemical potential differences in spin and then look at that. And I think that's still an open question. Yeah, but that's interesting. Yeah.
Yes.
Can you say again why the wave function falls off more slowly around the node?
Yeah. So basically, if you look at any point between the two nodes, right, you have a gap in your band structure, and that gap is essentially that gap gives you a cutoff on the length scale. So the length scale over which the wave function decays goes like 1 over the gap. And then as you come toward the nodes, the gap vanishes, so it starts to essentially penetrate the bulk.
All right. Let's thank Nandini again. We have longish coffee time.